So the previous session we have seen about various methods of producing interference pattern by division of wavefront. What we have seen is one this Young's double slit experiment, Fresnel biprism, and Lloyd mirror. These are the three things we have seen. And in this double slit experiment, what is happening actually? We are taking two waves with some difference. Let's say the wave entering slit 1, let's say it is represented as y1 is equal to a sin omega t, and y2, the wave entering through slit 2 is a sin omega t plus phi. So what are the assumptions we are considering here? The amplitude remains same in both the slits. A is same for y1 and y2. We are not using a1 and a2. We are considering it as a. And omega t frequency is same for both. The only difference is in phase, because the both waves are generated from a single source. So the amplitude is same. We are not dividing amplitude, we are only dividing the wavefront. So amplitude is same and frequency is same. So the result is this: y is equal to y1 plus y2. So if you add both of them, what do you get? Sin omega t cos phi plus a cos omega t sin phi. Right. We go for an alternative version. Let's say instead of sin omega t, you have cos. A cos omega t and a cos omega t plus phi. So if you add both of them, what you get is 2a cos phi by 2 cos omega t plus phi by 2. This is the result that you get when I add both of them. So here the basic function, that whatever cos omega t, the waveform is almost same with phase factor variation, right? So omega t and omega t plus phi, when you add both of them, you get some term something like omega t plus phi by 2. And instead of a, amplitude is now changed to a cos phi by 2, to a cos phi by 2. So amplitude is now oscillating. Here the amplitude is constant. Amplitude means what? The maximum height that a wave can go. So in both the waves, for the incoming waves, the amplitude is constant. Whereas for the resultant wave, amplitude is oscillating. So what you get? You get so intensity is square of amplitude, which is 4a square cos square phi by 2. Okay. So what you get? When you get the cos square term, you get a wave something like that. So you get 4a square cos square phi by 2. So means what? At some points you have 4a square intensity, and at some points you have 0, 4a square, 0, 4a square. So like that the intensity varies. So if you take the pattern, 4a square, 0, 4a square, 0, 4a square, 0, 4a square. So like that you get a pattern like that. Actually, what was the original condition? You are taking two waves with amplitude A, and if you just add them, resultant amplitude, what you are seeing for constructive interference is this, right? 2A. 2A is amplitude and intensity is 4A square. So let's say I1 is A square, I2 is A square, intensity of first wave is A square, intensity of second wave is A square. If you add both of them, resultant intensity is what? 2A square. You should get 2A square if you just add the intensities. But what is happening here? These amplitudes are getting added up. Instead of intensities, amplitude is getting added up, and you got 4A square. But that 4A square is also modified with a cos square phi by 2. So what is the result? Actually, this 4A square, at some portion you have 4A square, and the next level 0. 4A square 0. So if you take the average over this, what is average? You have 4 terms of 4A square and 4 terms of zeros. Average is 2A square. So what is happening? If you take only intensity pattern, if you just add the intensities, the result is 2A square. If you just add the intensities, the result is 2A square. But this 2A square at some portion is now shifted to here. You got a 0 here, and it is shifted to the next level. And next one, again 2A square plus this 2A square is now shifted to here. So like that, interference pattern is redistribution of intensity. Not bringing any new intensities. Whatever existing intensity, 2A square, is redistributed into this format. 4A square cos square phi by 2. So, in total, interference is redistribution of intensity. So, that 2A square is redistributed to 4A square 0, 4A square 0, 4A square 0. Okay. So the next topic is interference by division of amplitude. Interference by division of amplitude. So here we try to divide the amplitude. Means what? We try to divide the intensity. Okay. So for that purpose, what we are doing here is, so when light falls on any material, a portion will be transmitted, a portion will be reflected. Okay. A little portion may be absorbed, that we can neglect. But most possibly we consider reflection and refraction. Absorption part is neglected. So let's say this is the angle of incidence angle of reflection is also the same, equal to angle of incidence. Angle of refraction, we may consider it as R. Okay, so what happens? The input intensity is now divided between these two. So let's say instead of incident ray is equal to I reflected plus I refracted. So the intensity will be distributed between the reflected ray and refracted ray. So here we are neglecting the absorbed part. There is no absorbed light. So now, so if you form a interference pattern between these two rays now, here if this interference pattern is formed, so it is called interference by division of amplitude. So we are using the principle of reflection and refraction to divide the amplitude. Okay, so now here the path difference between these two rays. So there is an incident ray and there is a ray that is refracted and then reach the other end. So now path difference between these two is what? So from this point onwards these two are same. Up to this point these two are same. The difference between ray 1 and ray 2 is what? Let's say if we call it as A, B, C, D, it is AB plus BC minus AD. Right? The difference between let's say ray 2 and ray 1. Path difference. But in optics, whenever you measure distances, you must include the refractive index also, because at some portions the ray is traveling with high velocity, and some portions when the medium is denser, light ray slows down. So we have to multiply with the refractive index of the material also. So here it is mu times AB, so it is mu times AB plus BC minus 1 time AD. So that is the path difference. So this is most important. Wherever you come across distances in optics, you must multiply with refractive index of the medium. So this is called optical path length. This is called geometrical path length. So just by geometry we have measured this AB plus BC minus AD. This is the geometrical path length. Whereas this one is optical path length, where we are considering the refractive index of the medium also. Okay? So if you consider this thickness as T, this path difference will be equal to 2 mu T plus R. Path difference is 2 mu T cos R, and we have to consider additional path difference due to reflection. So here this reflection is taking place on a denser medium, right? So there is a additional path difference of lambda by 2. here the other end is air. Let's say this is glass plate, this is air. So here 0. Rarer medium, other end is a rarer medium. So additional path difference is 0. So in total, the total path difference that we observe here is true path difference is 2 mu t cos r plus 0 minus lambda by 2. In the first part you have 0, second part you have lambda by 2, and you are subtracting. So it is 0 minus lambda by 2. So that is the true path difference. So now condition for constructed interference is path difference is equal to n lambda, and destructive interference condition is path difference is equal to n plus half lambda. N lambda plus lambda by 2. So what do you get here? 2 mu t cos r is equal to n plus half lambda. Constructive interference. Destructive interference, 2 mu t cos r is equal to this lambda by 2 comes here. N lambda. N plus 1 lambda, which can be written as n lambda for a different set of values for n. So here n starts from 0, 1, 2, 3. Here also n is 0, 1, 2, 3. Here it is n is equal to 1, 2, 3. If you write n lambda, n value we take 1, 2, 3. Here it is, it starts from 0. So the basic condition, the first fringe is dark because of this additional lambda by 2. You get destructive interference. So one wave has a 0 path difference, the other is additional lambda by 2. So you get the first condition is dark. The first fringe is dark. So next one, we can consider the reflection on a thin film during transmission. Interference pattern transmission case. So here we are considering interference in reflection case. So if we consider interference during transmission, so what is the case? So this is one wave, reflected part. A part is transmitted and it will get reflected again. First reflection, a part is transmitted, and on the second surface, a part is reflected and a part is transmitted. Again, a part is transmitted, this we are not considering here. A part is reflected here on this surface. Again, transmission, a part will be reflected, we are not considering that. Our main focus is on the two transmitted rays. Okay, so now what is the path difference? What is the common portion and up to what location the waves are common, and where onwards the waves are different. So this point onwards the waves are same. Both are traveling same distance in same direction and same medium. So now the path difference. Up to this point, both are same. So I call that as A, B, C, D. Again the path difference is AB plus BC minus AD. Right? So now, so path difference is 2 mu t cos r. What about additional path difference? So we have to look for the reflections. So how many reflections are taking place here? Here the incident ray transmitted, again transmitted. So this is the ray 1. Next one reflection here, second reflection here, then transmission. So for the first reflection, what is the path difference? So the reflection is taking place from glass on air. So the second medium is air. So it is rarer medium. So path difference is 0. So if any wave reflects on rarer medium, 0 path difference. Here also, during this reflection, from glass into air, 0. So the additional path difference is 0 plus 0. So all you get is path difference is 2 mu t cos r. So constructed interference condition is 2 mu t cos r is equal to n lambda, and destructive interference condition is 2 mu t cos r is equal to n plus half lambda. So if you see, the condition for constructive interference in reflection is now the condition for destructive interference in transmission. Condition for destructive interference in reflection is same as constructive interference condition in transmission. So whatever pattern that you see during reflection, let's say the interference pattern in reflection is this. The transmitted wave pattern will be, it is just so wherever you have constructive interference, you get destructive here. If you have bright fringe in reflection, you will get a dark fringe in transmission. If you get a dark fringe in reflection, you get a bright fringe in transmission. So here also it is just a redistribution of intensity. So whatever total intensity, if you add both of them, you get 4A square intensity. Right? So it is redistributed between reflection and transmission cases. So now we'll consider the special cases, like what happens if we consider white light. So this is monochromatic light. So this is, let's say, this is the first order spectrum. Okay. Let's say for n is equal to 1, you got a condition for, let's say, some 3000 angstroms. And for n is equal to 2, that becomes 6000 angstroms. So when n becomes 2, at some point, we will get 6000 angstroms. So like that, okay. We'll see, let's say the light source is white. For some angle of incidence, some color got condition for constructive interference. Okay. What color it could be? Let's say this is blue. Okay. Now, if you shift the location to next level, I is increased. So when I increases, what happens? R also increases. I increase, R also increased. So condition for constructive interference, lambda also increases. So at this level you may get green. Higher wavelength. So if you shift the location to next level, you may get condition for red. And next set again. So if the angle increases further, you may get condition for n is equal to 2 blue. So this is increased further. So let's say this is 3000, 5000 and 7000. Maybe in between also you may get a condition for blue. Blue again. Blue, green 2, red 2. So like that you'll get second order spectrum. So that is how, if you use white light, so different locations of the film will be visible with different colors. So at some point you may get constructive condition for blue, next level green, next level red, like that the pattern continues. So once one set is over, you may get the condition for second set for n is equal to 2. So like that you'll get different colors on thin films. So that is what we say on soap bubbles, oil films and water. So all these colors on thin films are because of this white light interference on thin films. Okay. Another case, when thickness is very low, when T tends to 0. When T tends to 0, what happens? All visible colors may get diminished, and we may get only one option, lambda by 2 will be left. So when T tends to 0, you get darken reflection. When T tends to 0, n becomes 0, and entire film looks dark. Dark means what? There is no reflected light. The reflected light intensity is 0. Darker reflection, so that implies all light transmits. So when the reflection part is completely dark, entire light will be transmitted. So that thing, these things we use in non-reflective coatings. It's like our camera lenses. So it should absorb the entire light. Let's say night mode cameras. So it should absorb whatever minute amount of light that is coming in. So in that case, what we have to do? We have to use a very minute thickness film on the lens. What happens? N becomes 0. All we get is only lambda by 2 path difference, which is destructive interference. So entire light and reflection is destructive. You get dark fringe and destructive, dark fringe and reflection. So entire light will be transmitted. So you get complete light entering into the camera. So that is what we use in non-reflective films. What is the condition? The thickness should be minimally low. So when the thickness is very small, we get non-reflecting film. And when you use white light, you get all the colors. Okay. So So next one is extended light source. So here light source is a point light source, and to observe the interference pattern, the observer has to shift to different locations. Observer ikkada oka chote, ikkada oka chote, ikkada oka chote ila shift ayi chestu tappa in different colors ana manaku kanapadu. Whereas if you consider an extended light source, let's say the light source is like this. Okay, so now observer is sitting here. Let's say this location. So different portions will get different angles of refraction. So now here this is blue, this is green, this is red. Lower angle of refraction, little higher and little more higher. So if the light source is extended, the interference pattern at different locations on the film can be observed from a single location. Whereas if the light source is point source, observer has to move from one end to other end to see the interference pattern. Okay, so this is the basic principle we use in Newton Rings experiment. We use extended light source. And another adjustment, if the film is a bit slant, if the two layers are not parallel, if they are making an angle alpha, the equation becomes 2 mu t cos r plus alpha is equal to n lambda or n plus lambda by 2, n plus of lambda. And so if the upper and lower portions of bottom layers of the film are making an angle alpha, then the equation becomes 2 mu t cos r plus alpha. And conditions are the same. In reflection, n plus lambda by 2 is constructive interference, n lambda is destructive. And in transmission, n lambda is constructive, n plus of lambda is destructive. Okay, so the only difference is r plus alpha. Okay. So for a wedge shaped film with an wedge angle alpha, the path difference is 2 mu t cos r plus alpha, which may be equal to n plus half lambda n lambda for constructive and destructive in reflection, and this may be equal to n lambda and n plus half lambda for constructive and destructive in transmission. Okay, so now we consider the case of normal incidence. On air film. So I is equal to 0, R becomes 0. Air film annaru kabatti refractive index is 1. So equation ఏమవుతుందంటే 2t cos alpha is equal to n plus half lambda. Okay, and we also assume alpha is negligibly small. So alpha is negligibly small. ఏమవుతుందంటే cos alpha is 1. So we're imposing 3 conditions. Normal incidence I equal to 0, R becomes 0. Air film so refractive index becomes 1, and angle of wedge is negligibly small. So alpha is nearly 0, then cos alpha becomes 1. So then 2t is equal to n plus of lambda. Okay, so here the t value is increasing from point to point. Let's say this is t1 and this is t2. And if you extend this further, let's say this is O, A, B, C, D. Okay. Let's say these T1, T2 are consecutive fringes. Let's say one is dark and another is bright. Two consecutive fringes. So then, what do you get? Let's say 2 T1 is n plus half lambda. Then 2 T2 is n lambda. The difference is what? Here n is 1, here n is 0. So this is n lambda, I mean 1 lambda, this is lambda by 2. Difference is lambda by 2. So here n starts from 1, here n is 0. So this is plus lambda by 2, this is 1 lambda. Difference is plus lambda by 2. So T2 minus T1 is lambda by 4. Otherwise, if you take two bright fringes, let's say we consider two bright fringes. So T1 is for n is equal to 0 and 2 T2 n plus half lambda n is equal to 1. Then 2 T2 minus T1 is what? Lambda. N is 1. So 3 by 2 lambda, n is equal to 0, 1 by 2 lambda. So 3 by 2 minus 1 by 2 is 1 lambda. Right? So T2 minus T1 is lambda by 2. One condition. And another is, let's say, tan theta, tan alpha. So this is alpha. What is tan alpha? y2 minus y1 by x2 minus x1. Right? So y2 minus y1 by x2 minus x1, which is t2 minus t1 by ob minus oa. Okay, so tan alpha is equal to T2 minus T1 is lambda by 2. OB minus OA is beta, fringe width. Right? So the fringe width is given by, so fringe width is lambda by 2 tan alpha. So that is the fringe width. Or you can even write which may be when alpha is very small, it is lambda by 2 alpha. So what is tan alpha? Maybe whatever x distance by thickness of the film. I mean thickness by x. Okay, so let's say you have placed a wire between two glass plates. Okay, let's say this distance is x and this is diameter. Then tan theta is, or tan alpha is what? Let's say this is alpha, opposite side by. Then fringe width is what? Lambda by 2d by x. Lambda by 2d by x. Okay. And the fringe width, or if you want the diameter of the wire, okay. So if you want the diameter of the wire, d is equal to lambda x by 2 beta. So if you measure the fringe width, you can get the diameter of the wire. So here you are placing a wire of diameter d at a distance x from the origin. Okay, so now we use the same condition for a circular glass plate. So here these two are plain glass plates. So let's say this is a plain glass plate. So you get fringes like this. Instead of plain glass plate, you take a circular glass plate. So one is plain, another is plano-convex. One is plain glass plate, another is plano-convex glass plate. So now the light is incidenting normally. So what happens? It will get refracted. Some angle, let's say. So up to this portion is not a problem. There is a refraction here, because the incident angle is different here on the bottom surface. So up to top surface, it is normal incidence. So light rays are coming normally, perpendicular to the surface. So now there is a small angle here. So there is a refraction, another refraction. The interference pattern will be between these two light rays. One is reflecting on the top portion of plano-convex lens, another is reflecting on the top portion of plain glass plate. Okay, and we are using the same condition, 2 mu t cos r plus alpha. Is equal to, we are considering reflection, so n plus half alpha constructive, n plus half lambda is constructive, n lambda is destructive. Okay, so here the material is air. R is 0, alpha is negligible, so 2t is equal to n plus half lambda constructive, n lambda is destructive. So we have to get the thickness of the glass plate at this location where the interference pattern is produced. Okay, so that thickness is given by, so to get the value of the thickness we have to complete this circle. So let's say so here we are considering a small geometric construction. So let's say this is R and this is small r and this is T. Okay, so ఈ distance r అనుకుంటున్నాము. So this total distance is 2r minus t. ఇది r 2r minus t, 2r minus t and t. సో ఇక్కడ జరిగేది ఏంటి అంటే this r square is equal to 2r minus t multiplied by t. Product of the chord sectors, chord sections will be equal. So r square is equal to 2r minus t multiplied by t. So what do you get? R square is equal to 2rt minus t square, and that t square can be neglected for small values. It is 2rt. So t is equal to r square by 2r. So somewhere you can see some kind of derivatives here. R square derivative is 2r. So here you require a term with dimensions of distance. ఇక్కడ మనకి డిస్టెన్స్ కావాలి. ఒక పక్క ఏమో స్క్వేర్ ఉంది, రెండవది స్క్వేర్ ఉండదు. సో you are taking a ratio of distances. One is with square, another without square. Okay, r square 2r. So since t is very small, you should get a smaller number on numerator and a bigger number on denominator. So it is a small r square by 2 capital R is t. So in total it is so r square by r. So there is a 2 and these two will get cancelled. R square by 2r is equal to n plus half lambda or n lambda. And if you include mu also, mu will sit here. Okay. R square by r is equal to n plus half lambda or n lambda. So if you take two consecutive, so r square by r is equal to let's say you are taking two different rings, one mth ring and nth ring. R m square is m lambda and r m square by r is equal to m lambda. So if you take the difference, what do you get? Rm square minus Rn square by r is equal to m minus n lambda. Okay, so Rn square minus Rn square by r is equal to m minus n lambda. And if you consider diameter of the ring, it is twice the radius. So what can you write? So d m by 2 whole square minus dn by 2 whole square by r is equal to m minus n lambda. Right? So in total dm square minus dn square by r is equal to 4 lambda into m minus n. So if you want lambda, it is what? Lambda is equal to dm square minus dn square by 4 lambda r. So 4r into m minus n. Okay. So the equation is this: r square by r is equal to n lambda. R square by r is equal to n lambda. So if you consider diameter, it is dm square by 2 whole square. So you'll get a 4 dm. Okay. So where do you have that mu, if at all, if it exists? Mu ekkadiki vastundandi? Mu is in multiplication with r square. So dm square ekkada unte akkada manaku oka mu vastundi. Okay. So that is the situation. So this diameter of the ring d square is proportional to what? Lambda. So if you write d square is proportional to lambda, diameter is proportional to lambda, diameter is inversely proportional to refractive index, d square is proportional to r. ఇప్పుడు ఇందులో నుంచి d square is proportional to lambda, d square is inversely proportional to d square is proportional to r. So if the radius of curvature increases, diameter of the ring increases. If wavelength increases, diameter of the ring increases. So ఏమవుతుందండి, బ్లూకి స్మాలర్ రింగ్స్ వస్తాయి, గ్రీన్కి కొంచెం బిగ్గర్ రింగ్స్ వస్తాయి, రెడ్కి ఇంకా బిగ్గర్ రింగ్స్ వస్తాయి. అలాగే రిఫ్రాక్టివ్ ఇండెక్స్, ఎయిర్ ఉంటేనేమో ఒక రకం రింగ్స్ వస్తాయి. వాటర్ తీసుకున్నారు, ఏమవుతుందండి, వాటర్కి లెట్స్ 1.3 ఉంది డినామినేటర్లో, సో రింగ్ డయామీటర్ తగ్గిపోతుంది. ఇంకొకటి ఏదో థిక్ లిక్విడ్ ఆయిల్ ఏదో తీసుకున్నారు, రింగ్ డయామీటర్ ఇంకా తగ్గిపోతుంది. రైట్? అలాగే రేడియస్ ఆఫ్ కర్వేచర్, ఇఫ్ ద లెన్స్ ఇస్ మోర్ వైడర్ అండ్ వైడర్, you get bigger and bigger circuits. And the last topic in this interference series is Michelson Interferometer. So here we have a light source from which a parallel beam of light rays is being generated. So we are generating a parallel beam of light rays. And this parallel beam of light rays are falling on a beam splitter. So this is called beam splitter. Beam splitter that splits the light rays into two parts. So here the light rays will reflect on the bottom portion of this partially silvered glass plate. So this is a partially silvered glass plate. So its job is to split the beam. So the light beam will reflect on the bottom portion of this glass plate. So a portion will be reflected, a portion will be transmitted. Okay, we use two more mirrors, 100% silver. Here also 100% silver. So the light rays will be reflected back, and they both merge together here, and interference pattern is formed. Okay, so now what is the situation here? One light ray is reflecting from this glass plate. Second light ray is reflecting from the beam splitter and again from the 100% silver glass plate mirror. And finally it is contributing to interference pattern. So condition for construct interference, let's say delta is the path difference. Construct interference condition ఏమవుతుందంటే సో ఇక్కడ ఫస్ట్ వేవ్ తీసుకుందాం. లెట్స్ సే దిస్ ఇస్ ద ఫస్ట్ వన్ ఆన్ ఏ గ్లాస్ ప్లేట్ లాంబ్డా బై 2. సెకండ్ వన్ కి ఒక గ్లాస్ ప్లేట్ మీద అవుతుంది, ఇక్కడ ఒక లాంబ్డా బై 2 వస్తుంది. సో టోటల్ 2 - 1 ఈ సెకండ్ రేకి రెండు లాంబ్డా బై 2 కంట్రిబ్యూట్ అవుతాయి, టోటల్ లాంబ్డా ఫస్ట్ లాంబ్డా బై 2. And all these distances are same. Let's say this is O A and OB, plus OB, lambda plus OB, lambda by 2 plus OA. These two are equal, they get cancelled. OB and OA are equal, so they get cancelled, they will be left with lambda by 2. So the first fringe is dark. ఒక ఎక్స్ట్రా లాంబ్డా బై 2 ఉంది కాబట్టి ఫస్ట్ ఫ్రింజ్ డార్క్ ఉంటుంది. అదే సేమ్ మనకి న్యూటన్ రింగ్స్లో కూడా ఏం జరుగుతుందంటే ఎక్కడెక్కడ జరుగుతుంది రిఫ్లెక్షన్? ఫస్ట్ రిఫ్లెక్షన్ is on the bottom portion of curved glass. అంటే ఏముంది, కింద ఎయిర్ ఉంది కాబట్టి ఇక్కడ 0 వస్తుంది. ఇక్కడ గ్లాస్ ప్లేట్ మీద పడుతుంది. ద రిఫ్లెక్షన్ ఈజ్ ఆన్ ద టాప్ పోర్షన్ ఆఫ్ ద ప్లేన్ గ్లాస్ ప్లేట్. సో ఇక్కడ ఒక లాంబ్డా బై 2 వస్తుంది. సో హియర్ ద సెంట్రల్ ఫ్రింజ్ ఈజ్ డార్క్. సెంట్రల్ ఫ్రింజ్ అనేది డార్క్. అదే న్యూటన్ రింగ్స్ ట్రాన్స్మిషన్ కేసు తీసుకోండి. ట్రాన్స్మిషన్ ఎట్లా వస్తుందంటే ఇక్కడ ఫస్ట్ రే ఏమో డైరెక్ట్గా వచ్చేసింది బయటకు 0. సెకండ్ రే ఏమవుతుందంటే ఇక్కడ గ్లాస్ మీద రిఫ్లెక్ట్ అవుతుంది లాంబ్డా బై 2, ఇక్కడ కూడా గ్లాస్ మీద రిఫ్లెక్ట్ అవుతుంది లాంబ్డా. సో టోటలీ లాంబ్డా అంటే ఏమవుతుంది, లాంబ్డా అంటే మళ్ళీ కన్స్ట్రక్టివ్ ఇంటర్ఫరెన్స్ అవుతుంది. సో సెంట్రల్ ఫ్రింజ్ ఈజ్ బ్రైట్. సో హియర్ ఇట్ ఈస్ సెంట్రల్ ఫ్రింజ్ ఈజ్ బ్రైట్. So Newton rings during reflection case central fringe is dark and transmission case central fringe is bright. So ikkada kuda central fringe is dark and we see circular fringes. Both glass plates are parallel but still we see circular fringes. Circular fringes ఎందుకు వస్తాయంటే బికాస్ ఆఫ్ ద షేప్ ఆఫ్ దిస్ ఐ పీస్ ఆర్ షేప్ ఆఫ్ అవర్ ఐ. మన ఐ సర్క్యులర్గా ఉండటం, ఈవెన్ మనకి రెయిన్బో సర్క్యులర్గా కనపడటానికి కారణం ఏమైంటుంది, రెయిన్బో ఇట్లా ఆర్చ్ లాగా, ఇట్ ఈస్ ద షేప్ ఆఫ్ అవర్ ఐలెట్స్. మన కన్ను సర్క్యులర్గా ఉండటం వలన ఆ కండిషన్ ఫర్ whatever a thin film angle of incidence, angle of refraction, ఆ కండిషన్ అనేది మనకి సర్క్యులర్గా వచ్చింది. ఇక్కడ కూడా మనం ఒక ఈ సర్క్యులర్ లెన్సెస్ యూజ్ చేస్తున్నాం కాబట్టి ద ఫ్రింజెస్ ఆర్ సర్క్యులర్, తర్వాత గ్లాస్ ప్లేట్స్ ఆర్ ప్యారలల్. సో మనకి సో అంటే ఏమవుతుందంటే దీని యొక్క వర్చువల్ ఇమేజ్ అనేది, సో యూ కెన్ మూవ్ దిస్ ప్లేట్ అప్ అండ్ డౌన్, దీన్ని పైకి కిందకి మూవ్ చేయొచ్చు. సో యూ కెన్ అడ్జస్ట్ ద సపరేషన్ బిట్వీన్. సో దిస్ ఫార్మ్స్ ఏ వర్చువల్ ఇమేజ్ హియర్. సో లెట్స్ సే దీన్ని M1 అనుకుంటే M1కి సంబంధించినటువంటి వర్చువల్ ఇమేజ్ ఇక్కడ వస్తుంది, M2 అక్కడ ఉంటుంది. సో రెండు మెర్జ్ అయిపోతేనేమో మనకి ఎటువంటి ప్యాటర్న్ ఉండదు. ఇఫ్ దర్ ఇస్ ఎ గ్యాప్ యూ గెట్ ఎ ప్యాటర్న్. లెట్స్ సే దిస్ ఈజ్ M2 and this is M1 dash. You get circular fringes. Central fringe is dark, other fringes are bright and dark alternately. And if they are crossed, you get straight lines. Okay. And that's all. So if they are about to cross on this end, then the curvature will be in this direction. So if they are about to cross in this direction, then the curvature will be in this direction. So if they cross, you get parallel fringes, straight lines. Okay, so you can adjust the orientation of these mirrors. I mean, they can be set parallel or they can be set at an angle. If they are set parallel and separation is uniform, you get circular fringes. And if you keep on increasing the separation, you can get dark and bright fringes alternatively at the central location. So at initial condition is central fringe dark. If you increase the separation a little more, central fringe becomes bright. I mean, if this separation is increased by lambda by 4. ఈ separation lambda by 4 పెరిగితే ఏమవుతుందండి, లైట్ వెళ్ళి రావడానికి lambda by 2 ఎక్స్ట్రా పాత్ డిఫరెన్స్ వస్తుంది. Okay, so if the separation keeps on increasing in the multiples of lambda by 4, this bright and dark fringes will change. In the multiples of lambda by 4, additional path difference will be in the multiples of lambda by 2. So you get dark and bright fringes alternatively at the central location. So in the first case, the central fringe is dark. That's all. The last observation in Newton rings is this: r square by r is equal to n lambda. Rn square by r is equal to n lambda. So area of each ring is constant. So Rn plus 1 square minus Rn square is n plus 1 lambda minus n lambda. Rn plus 1 square minus Rn square by r is equal to lambda. So multiply by pi. So pi Rn plus 1 square minus Rn square is equal to pi lambda r. So an plus 1 minus an is equal to pi lambda r. So area of all the rings is equal. So if the area of the central ring is equal to area of the next ring. So width of the ring reduces as you go to higher and higher orders. So that, I mean, just like a gasket. ఈ కుక్కర్లో గ్యాస్కెట్ ఉంటుంది కదండి, దాన్ని మీరు స్ట్రెచ్ చేసుకుంటూ పోతే ఏమవుతుంది, విడ్త్ తగ్గిపోతూ ఉంటుంది, బట్ ద మెటీరియల్ రిమైన్స్ సేమ్. సో హియర్ ఆల్సో ఏరియా ఆఫ్ ఆల్ ద రింగ్స్ ఆర్ ఈక్వల్, but as the radius increases, the thickness of ring reduces.